Today, we'll dive into the early beginnings of AI, explore the contributions of some of its founding figures, and discuss the development of artificial intelligence techniques in the 21st century. Let's begin. Artificial intelligence has emerged as a prominent field of research and application, dramatically influencing various aspects of society. To fully comprehend the significance of AI, it is essential to delve into its early beginnings. The field of artificial intelligence can be traced back to the 1950s, with its roots intertwined with the development of computer science. While the concept of AI was not yet formalized, early researchers aspired to create machines that could replicate human intelligence. Alan Turing, a British mathematician and computer scientist, made significant strides in AI's initial stages by theorizing the concept of machine intelligence. In his seminal work, Computing Machinery and Intelligence, Turing introduced the imitation game, now famously known as the Turing test, which aimed to determine a machine's ability to exhibit human-like intelligence. Turing's work laid the foundation for the AI field and inspired future research on machine learning and natural language processing. The paper Artificial Intelligence in Knowledge Management, Overview and Trends presents a comprehensive analysis of the role of artificial intelligence in knowledge management and outlines the current trends in the field. The authors emphasize the importance of AI techniques in managing the growing volume of data and extracting valuable insights from it. The paper begins by explaining the core concepts of knowledge management, such as knowledge creation, storage, sharing, and application. It highlights the challenges in knowledge management, including handling the vast amount of data, the need for effective search and retrieval techniques, and the difficulty of representing and storing knowledge in computer systems. The authors then introduce the role of artificial intelligence in knowledge management, highlighting the advantages of artificial intelligence techniques in addressing the challenges faced by knowledge management. Artificial intelligence techniques can assist in capturing and representing knowledge, automating reasoning and learning processes, and providing intelligent decision-making support. The paper provides a detailed overview of the various AI techniques employed in knowledge management, including expert systems, natural language processing, neural networks. Expert systems are a branch of artificial intelligence that aims to replicate the decision-making abilities of a human expert in a specific domain. They are computer programs designed to solve complex problems by utilizing knowledge representation, reasoning, and inference techniques. Expert systems have been used in various fields, such as medicine, finance, engineering, and environmental management, to provide valuable insights and decision-making support. The knowledge base is a repository of domain-specific facts, rules, and heuristics gathered from human experts. It contains both explicit knowledge, e.g., established principles, relationships and definitions, and tacit knowledge, e.g., intuitive judgments, experiences, and problem-solving strategies. The knowledge base is essential for an expert system, as it serves as the foundation for reasoning and decision-making processes. The inference engine is the component that processes and manipulates the information stored in the knowledge base. It uses various reasoning techniques, such as forward chaining, backward chaining, or a combination of both, to deduce new knowledge or conclusions based on the existing data. The inference engine plays a vital role in the expert system's decision-making process, as it allows the system to simulate the problem-solving approach of a human expert. The user interface should be designed to be intuitive, user-friendly, and easily accessible, enabling users of various expertise levels to interact with the expert system effectively. The user interface may include features such as natural language processing capabilities for understanding and processing user queries, graphical representations of the problem domain, or visualizations of the system's reasoning process. It may also offer interactive features, such as guided questionnaires, to help users provide the necessary information for the expert system to make informed decisions. An essential component of an expert system is the explanation facility, which allows the system to justify its conclusions or recommendations. This feature is critical in fostering user trust and understanding of the expert system's decision-making process. The explanation facility can provide users with a step-by-step explanation of the system's reasoning, underlying assumptions, and the knowledge or rules applied. It may also offer alternative solutions or recommendations, along with the rationale for selecting a particular course of action. Natural language processing is a subfield of artificial intelligence and linguistics that focuses on the development of algorithms and techniques to enable computers to understand, interpret, and generate human language. Natural language processing serves as an intersection between computer science, human language, and machine learning, aiming to bridge the gap between human communication and computer understanding. The ultimate goal of natural language processing is to create intelligent systems that can effectively process and analyze large volumes of natural language data, enabling improved human-computer interaction and facilitating the extraction of valuable information from textual sources. Parsing is the process of determining the syntactic structure of a sentence or text. This may involve generating a parse tree, which is a hierarchical representation of the grammatical relationships among the words in a sentence. Parse trees can help to identify the subject, object, and verb of a sentence, as well as other syntactic elements like phrases and clauses. Parsing is essential for various NLP tasks, such as semantic analysis, machine translation, and information extraction. Neural networks, often referred to as artificial neural networks, are a class of machine learning models inspired by the structure and functioning of the human brain. They are designed to recognize patterns, learn from data, and make predictions or decisions. The primary building blocks of neural networks are artificial neurons or nodes, which are organized into interconnected layers to form a network. Neural networks have gained prominence in various fields, including computer vision, natural language processing, speech recognition, and robotics, due to their ability to model complex, nonlinear relationships in data. Artificial neurons, or nodes, are the fundamental units of a neural network. Each neuron receives input from other neurons or external sources, applies a weighted sum to the inputs, and then passes the result through an activation function. The activation function introduces nonlinearity into the model and determines the neuron's output. Neural networks consist of multiple layers of interconnected neurons, typically organized into an input layer, one or more hidden layers, and an output layer. The input layer receives the data, while the hidden layers perform the computations and transformations. The output layer produces the final predictions or classifications. Weights and biases are adjustable parameters within the neural network that determine the strength of the connections between neurons. During the training process, the weights and biases are adjusted to minimize the difference between the network's predictions and the actual target values. Activation functions are mathematical functions that introduce nonlinearity into the neural network model, allowing it to learn and approximate complex relationships between inputs and outputs. They determine the output of a neuron based on the weighted sum of its inputs. Activation functions play a crucial role in the learning process, as they help control the flow of information through the network and influence the model's ability to converge to an optimal solution.
Goodbye.